All right, well, have a little homework back for you today. And you did have one problem. I think it was to do something similar to a proof that we did last time. Yeah, I think it's the same pattern. This one is a pretty kind of a copycat kind of thing. You like those kind of exercises?
I know how to do it.
Yeah, so all I have to do is just switch one letter for another letter and you do it. Anyway, so I assume there's no questions about that. It sounds like there's no questions. Okay, so today we're going to start a new topic, combinatorial analysis. All right, I wish we had a chance to do the entire chapter, but we'll only do the first section or two. So this combinatorial analysis is about counting. All right, so everyone knows how to count. 1, 2, 3, 4. Well, except that sometimes when you ask to count occurrences of things, it can be a little tricky. So we're going to start off here. Okay, so let's take a look at our equation sheet under the section combinatorial analysis, and we see the first three rules that we will learn are the rule of sum, the rule of product, and the rule of difference. So let's see what that means. Okay, first of all, 16.1 is the rule of sum. So the size of the union of n finite pairwise disjoint sets is the sum of their sizes. You know, like if you have, here's one set and it has 3 things in it, and here's another set and it has 2 things in it, and these sets are pairwise disjoint. Right, let's have another set with 1 thing in it. Okay, so this is a different situation from this one, where this one has 3 and this one has 2 and this one has 1. Okay, so these are not pairwise disjoint, right? But these are. So what's the size of this one? 3. What's the size of this one? And what's the size of this one? 1. So 3 plus 2 plus 1 equals 6. That's the size of the union. So the union would be, you know, the union of all these. So the size of the union would be 6. But the only way is 3 plus 2 plus 1 equals 6. Here, the size of this one is 3, the size of this one is 2, the size of this one is 1. But the union only has 4, right? So the rule of sum says the size of the union of n finite pairwise disjoint sets is the sum of their sizes. And so that occurs here, but not here, right? Okay, so that's the rule of sum. Now the rule of product says, 16.2 says, the size of the cross product of n sets is the product of their sizes. Now I think this one, we already know this one actually, because what if this is, suppose this is the set S, and this is the set T, and this is A, B, C, and this is D and E. Then tell me, what is the set S cross T? This is all review. What is the set S cross T?
It could be AD, AE, BD, BE, CD, CD.
Yeah. It's a set of ordered pairs, right?
Yeah.
So it's A, D, A, E, B, D, B, E, B, D, B, E, and C, D, C, E. All right? So here, oh, bad example. 6 is the same here. 6 is here. I mean, I shouldn't use an example where this is 6 and this is 6. But anyway. So here it's 3 times, the number of elements in this set is 6, right? So this is 3 times 2 equals 6, right? So that's an example of the rule of product, the size of the cross product of n sets, and the product of their sizes. Because what we're dealing with here are pairs, you know, all the possible ordered pairs, right? And then 16.3 is the rule of difference. The size of a set with a subset of it removed is the size of the set minus the size of the subset. So here, if we have here's the set S, and here's and suppose it has, it's like this, and then let's suppose that we have a subset which is T, right? And so it says the size of the set with the subset of it removed. So with this subset removed, if this is a subset, right? So if that subset is removed, then what we have, what we're left with are these points. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So there's 6 minus 2 is 4. Pretty trivial, right? But, I mean, that's the way it is. Okay, but now the thing of it is that whether you use a sum or a product or a difference, that, I mean, you have to, well, the main thing about combinatorial analysis is you have to recognize when to use the sum and when to use the product and when to use the difference. Okay, but these visualizations are the basis, these set visualizations are the basis of the rules. Okay, so enough of this theory. Let's do some exercises. Now what I've done here is, for your convenience, for our convenience in the discussion here, these are exercises from the back of the book. All right? So here we have exercise. So let's do, let's just work through the first 3 of these exercises in the book to illustrate these rules. Okay, so here's the first exercise, 16.1. Suppose the campus bookstore has 10 texts on Fortran and 25 books on Pascal. Boy, you can tell that this book is old because Fortran and Pascal are both very old programming languages. Have you heard of either one of those?
Pascal, but not Pascal.
Yeah, Fortran is one of the, Fortran is quite an amazing language because it is one of the oldest, it was one of the very first programming languages invented, way back in the 50s. And yet, a variation of Fortran is still in widespread use today. So it's quite amazing. Fortran stands for Formula Translator, and in the very early days, computers were used primarily for numerical calculations, and so it's very math. And so all of the early math libraries were all written in Fortran, and they still are. And some of those early math Fortran libraries are still. They have evolved, and they're still in use today. So Fortran, most compilers come with a Fortran compiler, and Pascal is also very old, and it's still around. But it hasn't. Fortran, Fortran is quite an amazing language. But anyway, they're both very old. You can tell that the book is a little bit old on the example here. But anyway, suppose the campus bookstore has 10 texts on Fortran and 25 on Pascal. How many different Fortran or Pascal texts can a student buy?
35.
Yeah, the sum. So exercise 16.1. So in this case, you would use the rule of sum, and it would be 10 plus 25 is 35. But what about the second part of the problem? It says, how many choices are there to choose a pair?
Product.
Yeah, and so why is that? Why is that to choose a pair as a product?
Picking 2 things, and the first option you have 10 options.
And the second thing,
you have 25.
right. So basically, it's like an ordered pair of Fortran Pascal, right? So it's the cross product. Okay, so this would be the rule of well, just rule of product. How about so it's 10 times 25. So there's 250 ways to make that kind of selection, right? Okay, so that's an example of product, sum and product rules. Now, how about exercise 16.2? Okay, so suppose 15 bits. Ooh, you know what a bit is? What does bit stand for, by the way?
No idea.
Binary digit. A bit is a binary digit, and a binary digit can be either a 0 or a 1. Binary means 2, so it has 2 values. Actually, a byte is 8 bits. B-Y-T-E. Well, yeah, it stands for 8 bits. a BYTE equals 8 bits.
So this is a byte and 7 bits?
No, and it's BY, not BI. Okay, but that's 8 bits. But a bit stands for binary here. Bit
And then megabytes
stands for binary
that where that comes in?
digit, correct. So if you have MB, that is megabyte. So that's a million
Million
bytes, so which is 8 million bits. Yeah.
Kilobyte, 1,000.
And a kilobyte, yes, and a kilobyte is 1,000 KB, correct.
Terabyte.
Terabyte is a trillion.
Gigabyte.
Sorry, gigabyte
Gigabytes
is a trillion.
Not a trillion.
Wait, a billion. No, sorry.
Terabyte is 1,000 trillion. 1,000.
Yeah, each one is 1,000 more. It's kilo. Okay. As long as we're doing it, we better do it right. Okay, so here we have byte, we have kilobyte, we have megabyte, we have gigabyte, and we have terabyte. Okay, so this is 1,000. This is 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. It's actually approximately 10 to the 3 and 10 to the 9. But that's a discussion for another day. All right, so now, suppose 15 bits are used to describe the address of a memory location in a computer, each bit being 0 or 1. Oh, so he defines what the bit is there. How many different locations can there be? So okay, so here's the picture. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? So you can think of this, we can think of this as a container, and there's 15, 1, 2, count them, there's 15, right, of these little boxes, and each boxes can be either 0, 1, so this could be 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, something like that. The question is, how many possible patterns of zeros and ones are there?
Did you use like a permutation or something?
Well, what would you use? How would you? Yeah, now this is a really good. Yeah, how do you approach this? How do you know? How do you count how many possible combinations of zeros and ones there are in this box with 15 cells, each one of which can be 0 and 1? But it's which rule? But the question is what rule? It's the product rule, because this is instead of this being an ordered pair, it's an ordered what? Instead of being an ordered pair, it's an ordered what? No, not a set.
Ordered 15.
15 what?
Ordered list.
Tuple. Remember tuple?
Oh, man.
And
Yeah.
instead of being an ordered pair, it's an ordered 15 tuple. Are you with me? It's like the first one can be 0 or 1, the second one can be 0 and 1, and because it's an ordered 15 tuple, it's basically what?
2 times 2.
It's the cross product, right? So for each one of these, and you can think of it like, so it's the rule of product.
0, 1 times 0, 1.
Yeah, well, it's 2 possibilities for this, times 2 for this, times 2 for this. Are you with me? So it's 2 times times 2, and there's 15 of these. So it's 2 to the 15. Does everybody see how that works?
What's 2 to the 15?
2 to the 32K. 32K. 30, that's about 32,000.
About.
Yeah.
Oh, precision.
Well, all right. It's 1,024 times 32. That's how much it is. And that's about 32,000 because that's about 1,000. Are you with me?
Fair enough. That's nifty.
And 1,024 is 2 to the 10. That's what all computer scientists know. At one point, if you keep...
I guess I'm not a computer scientist.
No. I mean 2 to the 10. Okay, all right. Okay, here goes the K again. All right. So here we had K. Now a computer science K is 2 to the 10, which is 1024. Is 1,024.
Oh.
See, that's why it's not quite 1,000.
That's why you said
That's why I said it's about. It's not quite so whenever you're talking about memory in your computer and you say I have so many, M or G.
Someone says I have a megabyte. They really
It's actually 1,024. Well, yeah, and then a meg is 2 to the 20. All right, which is 1,024. If you work it out on your calculator, times 1,024.
Yeah, it's a large number.
Well, it's about a million,
About,
but it's 1 something. Anyway,
now we're all confused.
all right. So that's okay. So that's exercise 16.2. Let's do exercise 16.3. 8 men are auditioning for the lead male role and 6 women for the lead female role in a play. So right away, what do we know? It's an ordered what?
Pair.
It's an ordered pair. Male lead, female lead. So how many possible?
Making 2 decisions, but 6 times.
Yeah, and that's rule of product. Exercise 16.3, it's rule of product, which is, what do we say, 6 times, how many? 8? 8 times 6? That's 48, right? Are we good?
Ish.
Okay, now let's take a look at the others, 16.4 through 16.7. And let's see if we can understand how these work. Okay, so definition. Now, this definition is just a definition, right? P n r equals n factorial divided by n minus r factorial. All right, so that's just a definition. And then 16.5 says the number of r permutations of a set of size n equals Pnr. And 16.6 says the number of r permutations with repetition of a set of size n is n to the r. So let's explore those. First of all, let's understand or define what is a permutation. First of all, to do a permutation, we assume that the objects are distinct. Okay? So a permutation of a set of distinct objects, is an ordered arrangement of the objects. Okay? So the order counts. Is an ordered arrangement of the objects. Okay? And an ordered arrangement of R elements of a set is called an R permutation. That's what that definition is. An ordered arrangement of R elements of a set is an R permutation. So here, let's do an example. So now, order counts. So we're talking about ordered tuples, right? And so here's an example. D, A, E is a 3 permutation of this set. A, B, C, D, E, F, G. A, B, C, D, E, F, G. All right? So this is called a 3 permutation of this. So what happens, so here's the question. The question is, given this set of objects, how many ways, this is one 3 permutation, DAE. Now because this is ordered, you understand that ADE is a different R. So ADE is a different 3 permutation, right? Because the order counts.
Right.
Is a different 3 permutation. Are you with me? So this is a different one from this because the order counts, right? Okay, now so here's the question. How many possible 3 permutations are there of this?
N factorial divided by n minus 3 factorial.
Right, right. But and how can we, and how can we see, how can we see that that's the case? So let's ask the question: how many 3 permutations are there from a set of how many? 1, 2, 3, 4, 5, 6. How many 3 permutations are there? How many 3 permutations are there from a set of 7? So now here's one way to think of it. There's 2 ways to think of it. Here's the first way. Now watch this. Well, first of all, how many ways are there to pick the first one?
7, then 6.
Well, yeah, this first one could either be A, B, C, D, E, F, or G, right? So let's assume that we pick, like D for the first one, right? Like here, D, right? But then once we pick the first one, how many ways are there to pick the second one?
6.
Well, there's only 6 because there's only 6 left because you can't, it's an ordered arrangement of R elements, so there's no repeating here. Right? It's an ordered arrangement. So there's 6 ways to pick this. But then after you pick the A, how many ways are there to pick the third one? There's 5. Okay, so the answer is 7 times 6 times 5. That's one way to think of it. 7 times 6 times 5. Right? But another way to think of it is 7 times 6 times 5 is, there's another way to write 7 times 6 times 5, right? Another way to write 7 times 6 times 5 is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. Right? So this is 7 factorial over 4 factorial.
Which is 7 factorial over 7
Which is
3 factorial.
7 times 6 times 5.
Right, which is what we have here. So that's P, so now let's go back to that is P what?
7, 3.
7 3.
P73. Okay? Are we good?
Is that how you prove?
So 16.4 is the 16.4 is the generalization. So what we just illustrated was 16.5, the number of R permutations of a set of size n equals P n R.
Can you prove 16.5? It's not.
Okay, now how about 16.6? The number of R permutations with repetition. The number of R permutations with repetition is of a set of size n is n to the R. So what would be an example of that? Yes, after you've chosen what goes in the first one, if you can have repetition, that means that you can choose it again. Okay.
That's just 7 times 6.
Okay. So the 3 actually what are there? The 3 permutations. The 3 permutations of, let's just not have quite as big a set. Let's just go A, B, C, D. Yes, it is. Only this time instead of being binary, it's quaternary. Yeah. So what are we? If we were just to list them, we could if we pick A for the first one, well, it's okay to pick A for the second one, right? So you could do AAA, AAB, AAC, AAD, right? And so for picking this AA, there's 4 ways to pick the last one, right? But then for each one of these, there's 4 ways to do this and 4 ways to do this. And so we could continue ABA, ABB, etc. And the question is, how many? In this case, there's what? 4 to the third. So 16 times 4, which is whatever. Are we good? Okay, let's do the next one, 16.7. Now what does 16.7 say? The number of permutations of a bag of size n.
What's a bag again?
Size is how many elements?
Yeah, I mean, you can actually literally think of this as a bag, you know. I mean, a literal bag with objects in it. So the number of permutations of a bag of size n with k distinct elements occurring n1, n2, nk times is n factorial divided by n1 factorial times n2 factorial times times nk factorial. Holy moly.
We did bags and we did sets.
Yeah, we did bags when we did sets. It's where duplicates are allowed. It's sets where duplicates are allowed. Remember that? Actually, do you remember that? Do you remember?
The bag of BB equals BB, not B.
Yeah, the bag with BB is not equal to the bag with just B,
Yeah.
whereas the set is.
Set is, okay.
Yeah. Actually, do you remember this was the notation for a set? Do you remember what the notation for a bag was?
Oh, is it line?
There's a line there.
I remember forgetting this.
You remember forgetting it. That's good. I remember forgetting that.
Wow, that was last semester, wasn't it?
It was, because we did sets last
You
semester.
said, oh, this will come up one time.
Maybe I did say that. I don't remember. Okay, so let's do an example of 16.7. 16.7 example. All right, suppose we have a bag with 3 red balls, 4 green balls, and 2 white balls. Nice try. Okay, so you can imagine this. So if we were using our bag notation from last time, it would be like this. R, 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 G, 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 W, W. It would be like that. And furthermore, because this is not a set, I mean, if this was a set, this would be the same as just R, G, W. Because it's a bag, you can have duplicates. So that's why we use it. It's actually related to that. The question is, how many ways can you line up the balls? Well, the thing of it is that if they were distinct, if they had numbers on them, you know, like if this, yeah, I mean,
You can flip 2 reds.
you can flip 2 reds and it's the same thing. So you can't count.
You can't count that.
Yeah, and that's how you have to think about these problems. You have to think, are they distinct?
It's n factorial of the 4 factorial of the 3 factorial of the 2 factorial.
Yeah. Okay. Okay. So here, yeah. Let's work through this. So here's one way to line them up. Here's one way to line them up. R, 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 G, 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 W, W. That's one way to line them up. Now, if they were distinct, and let's make them distinct just for sake of argument. If they were distinct, so if they had numbers on them, if this was R1, you know, if they were like pool table balls, you know, so R1, R2, R3, G1, G2, G3, G4, W1, W2, then there would be how many ways? Well, how many ways would there be? Well, you could pick 9, you know. This is this would be, this is a special example, right? Of n, where n minus r, where n and r are the same. So n minus r here, let's look at 16.4. So n would be not, n and r would both be, how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9. So this would be 9 factorial divided by 9 minus 9 factorial. 9 minus 9 is 0. 0 factorial is 1. So this would be 9 factorial, right? So, and another way of thinking of that is there'd be 9 ways, 8, and then after you pick the first one, there'd be 8 ways to pick the second one. So if they were distinct, there would be 9 factorial ways. There would be 9 factorial ways. All right? But now here's the thing. Are you with me here? So in other words, this would be the same thing as, this would be different from this one. R2, so R2, R1, R3, G1, G2, G3, G4, W1, W2 would be a different permutation. Does everybody see that? I mean, if they were distinct, this one would be a different permutation from this one. But the trouble is they're not distinct. So if they're, in other words, the reds are all just red. There's no difference between one red and another. Of course, the reds are distinct from the G's, but still, the reds, you can't, in this situation, you can't tell one red ball from another one. So there's got to be more or fewer ways to do that. There's got to be much fewer. Well, how much fewer? I mean, how much fewer are there? How do I say this? By what? How far off are we when we say there's 9 factorial?
By the factorials of.
Yeah. Well.
And the factorials of the greens and the factorials of the whites.
Yeah. For each. Yeah, that's exactly right. So for each. In other words, how far off are we? By what factor off are we by virtue of the reds? Yeah, there's going to be 6. Yeah, we're off by a factor of 6. Right? If we count them as being distinct, we will count them. We'll have 6 times too many by virtue of the fact that the reds are not distinct. Yeah. So what do we have to do? We have to take that 9 factorial. We have to take that 9 factorial and do what with it? Divide it by how many permutations of the reds there are if they were distinct.
Right.
But then you can apply the same reasoning with the G's. So you also have to divide it by 4 factorial, and you can apply the same reasoning with the W's. So you'd have to divide that by however many permutations of 2 there are, right? So let's write that out. For a given permutation, let's go over here. We're off by, here's what we're off by. We're off by 3 factorial here, and we're off by 4 factorial here, and we're off by 2 factorial here.
6 divided by 6 is still 1, it's not 0.
Okay. So for a given permutation, the R's could be rearranged 3 factorial ways. For a given permutation, the R's could be rearranged 3 factorial ways. Okay? So the R's are not distinct. So if the R's are not distinct, 9 factorial overcounts by a factor of 3 factorial. So if the R's are not distinct, so if the R's are not distinct, the 9 factorial overcounts by a factor of 3 factorial. So basically, the number of ways is 9 factorial over 3 factorial, which corrects the overcount for the permutations of R, 4 factorial, which takes into account the overcounting by the possible permutations of the W's, and then 2 factorial. Now here's what's kind of amazing about this. This has to be an integer.
Yeah.
This can't be a fractional part.
Dividing by a number that's already in there.
Yeah, but it's interesting that these factorials are smaller. I mean, it's interesting that the 9, if you work this out and see what cancels, it's interesting that if you have any number, the factorial of any number down here, and you divide it by the factorial of a number that sums to this number, and the factorial of that will be an integer.
That's a theorem right there.
I mean, that's
proven.
I mean, that's kind of a remarkable fact, I think. Don't you think? Oh wait, did we go back? So 16.7 is the general case. The number of permutations of a bag of size n with k distinct elements occurring n times is this. All right? So now let's do exercise 1621. Here you go. So exercise 1621. It says, how many permutations of algorithm have the A, the L, and the G together
So it's 3
in any order?
It's 3 permutation. It's
Well, you have to use.
That's the whole word.
Yeah, no, yeah. Here you can't use a formula. I mean, you have to use the rule. I think this doesn't fit one of those general formulas. This, you have to go back to the rules, I think. How many permutations of, okay, so algorithm has how many letters in it? A, L, G, O, R, I, T, H, M. So there's 9 letters in algorithm, right? So let's write down some of the permutations that they're talking about. How many permutations have it together? So here's one possibility. Actually, A, L, G, O, R, I, T, H, M. Here's another one. I, T, M, G, A, L, O, R, H. Does that get them all? Now, does everybody see that? Here's one. Here's another one. Are you with me?
Yeah.
What's another one? Give me another super random one. H,
It's 7, choose 3.
H,
R-O,
R, O,
T,
huh?
T, M-I,
T, M, I,
7 factorial
What?
times 3
L, G, A.
yeah, sure.
That's another one, right? And why are these all included in our count? Because the G and the A and the L are all together in any order. And my question is, so my question is, how many of these can you write down? We just wrote down 3 ones kind of at random. How many different ones are there? Let's count. Combinatorics. Can you count that? How many?
7 factorial times 3 factorial.
Ooh, how'd you get that?
Because it's 7 different things that you're arranging, and then one of those things you can arrange 6 different times.
Yeah, that's a good insight. That's a good insight. Look at this. If we put our parentheses around here, and we put this parentheses around here, and we put this parentheses around here, what you...
Arranging the group, you can arrange those 3.
Yeah, see, now you got to start using reasoning without these formulas. Not everything is susceptible to just plugging into a formula. Yeah, so the insight is this. What you do is you consider this to be one letter. If you were to consider this to be one letter, then we would have a word with 1, 2, 3, 4, 5, 6, 7 letters, right?
That's mine.
So think of ALG as one letter. Think of...
I think we all did this like sophomore year.
If you guys like this, you'll love probability.
Think of ALG as one letter, in parentheses, as one letter, right? Okay, so then ALG, like this, ALG, ORITHM, has, okay, so then has 7 letters, right? And for each of these, and for each permutation of the 7 letters, there's what? There's a permutation of those. So that's the rule of what? For each of these, there are 3 factorial permutations of ALG. There are 3 factorial permutations of ALG. So by the rule of product, 3 factorial times 7 factorial. You guys have your calculators with you? You have factorial buttons?
I mean,
6,
You want to take a guess?
It's less than 9 factorial.
You want to do it in your head? 30,240. You were so close.
Yeah.
Okay, now so now the next one is and you may have seen this before. It's called the binomial coefficient. Actually, we do this as this is a favorite programming exercise because the binomial coefficient is there's a nice recursive algorithm for computing the binomial coefficient based on Pascal's triangle. You guys know Pascal's triangle?
Yes.
And 16.9 is a definition, and then 16.10 is a statement about how it applies. Okay, so here's the definition of the binomial coefficient. Now, by the way, you don't say n over r because n over r would be a fraction. Notice that there's not a line between the n and the r. So the way you say this is n choose r. Okay? N choose r. So the binomial coefficient n choose r, which is read n choose r, is defined by n choose r equals, now this time instead of having n factorial, yeah, what we have is n factorial over r factorial times n minus r factorial for 0 less than or equal to r less than or equal to n. Okay?
Different ways of arranging it.
Right. Okay? And now what we're saying is the number of r combinations of n elements is n choose r. So I guess it's time to quit. So we'll show you next time what an r combination. We'll give an example of 3 combinations. And we'll give an example of some r. See, before we were doing r permutations, right? So now we're going to do r combinations. Difference between an r permutation and an r combination
Order doesn't matter.
is that order doesn't matter. Yeah. Okay? So we'll finish, and we'll be able to easily finish this up next time, and then go on to the last one, which will be graphs. All right? See you tomorrow.